Hi everyone, welcome to yet another seminar on MIR. Today we have with us Krishna Subramani from IIT in Mumbai. In the past, Krishna has been a visiting researcher at the Music Technology Group at Kyoto University, where he's worked on MIR and statistical signal processing. Krishna will be graduating in August and will then begin a PhD at the University of Illinois at Urbana-Champaign. Variational Parametric Model for Audio Synthesis, which I believe was an ICAST paper. And Krishna, if you're ready, I'll just leave it to you.
Right. Okay. Thanks for the introduction. So, if anyone cannot hear me, you can just point it out in the chat window. So, okay. All right. I assume everyone can hear me. So, yeah. So, I'll be presenting our work on variational parametric models for audio synthesis. So this is work done with Professor Preeti Rao here at IIT Bombay and with Alexandre, an internship student with us from ENS Paris-Saclay. So the major thing to ask here is what is audio synthesis? So if you go to the 70s and the 80s, or even earlier, maybe in the mid 60s, and go and ask a music enthusiast what an audio synth was, he would most likely refer you to one of these modular synthesizers, which used analog electronics to synthesize audio. Then with the advent of digital computing in the early 80s and late 80s and early 90s, and even now actually, so a synth is something like this Yamaha synthesizer, which is a MIDI and a MIDI-based digital synthesizer, which either stores samples or does some kind of digital synthesis to synthesize the instrument sounds. But is there something next? Is there something beyond this? So with the advent of data-driven statistical modeling and computing power with GPUs, why don't we harness the tools of deep learning for audio synthesis? So we can rethink our idea of a generative synthesizer as something like this. So it is a data-driven black box model which takes in as input the control parameters like the timbre of the instrument, the pitch, and the loudness. So the timbre, just a quick reminder of what these are. The timbre is what makes a violin and flute sound different when they both play the same note at the same loudness. So that essentially stems from characteristic differences in the spectrum domain or in the temporal domain. So the pitch is just the fundamental frequency of the note being played, and the loudness is the intensity or the energy with which you bang the note on the keyboard. So just a brief review of generative models for audio. So the first people to use deep learning, not deep learning, but neural network-based autoencoder models were Saroff and Casey back in 2014. So where they performed frame-wise reconstruction of the short-time magnitude spectra with autoencoders. So they basically extracted the audio from the sustained, they extracted frames from the sustained portion of an audio note and computed the spectra and autoencoded it with, where the autoencoder was a simple feed-forward neural network. Roche more recently extended on this work and tried out different autoencoder architectures like recurrent autoencoders or variational autoencoders. And she also analyzed this audio latent space for its usability in the synthesis of new musical sounds. Essling, also around the same time, tried a different approach by trying to regularize this latent space for better control over the timbre of the synthesized instruments. So some issues with these frame-wise analysis synthesis-based methods were that since we are feeding the frames independent of each other, we do not feed any information of the temporal ordering of the frames to the network. So there is inherently no temporality in the audio. So you only model the sustained portion of the sound. And because we work with the spectral representation of the sound, we work with the Fourier transform. And if you perform any transformations of the audio, you only have the magnitude spectrogram to work with. So phase estimation becomes an issue when you try to invert the obtained spectrogram. So rather than working in the spectral domain, Engel in 17 in his NSynth work was inspired by WaveNet's autoregressive modeling capacities for speech, and he extended it to musical instrument synthesis. And in this work, he also introduced the massive dataset NSynth, which has enabled researchers to try out various other deep learning methods for a lot of audio tasks, not just synthesis. So Weiss in 2018 also proposed something similar, but rather than autoregressively modeling the audio, he proposed sample by sample generation with a recurrent neural network. And for better control over the waveform generated, he proposed to condition the samples on the additional parameters available, like the pitch, the velocity, and the instrument of the audio being played. And Defosse, instead of generating the audio samples, proposed frame-by-frame audio waveform generation with LSTMs. So all of these methods discussed so far have one commonality in that they work with audio in the raw form. So they either work with the waveform or with a 1-1 transform of the waveform, which is the spectrum. So what are the issues, or what we felt were the issues that arose with these methods were? So for the waveform methods, considering you were generating each individual sample, there were a lot of simultaneous time scales to consider, especially in musical audio instrument synthesis. So that inherently led to your architectures becoming very complicated. So for example, in NSynth's repository, Engel and his team have mentioned that to train they don't recommend researchers who don't have access to compute power to train their model, because it took them 5 days and I think 32 K40 GPUs. And each K40, if you assume, costs $5,000. It's a lot of money for training a single model. So that's the kind of resources giants at Google, Facebook, or Microsoft might be having, but that is certainly not the kind of resources we have here or in many other research places in the world. So, and as mentioned, an issue with the spectral methods was the phase estimation issue. So why parametric? Why move on to a parametric representation? So the advantage a good parametric model gives us, and by good I mean a parametric model that actually satisfies or can be used to estimate the data in a better way. The advantage that this gives us is we can model a reduced parameter space over the waveform or spectrum instead of directly modeling in the original high-dimensional space of the waveform or the spectrum. And if we combine this with the generative modeling capacities of a neural network, we can, in theory, use simpler architectures, lesser data, and be able to better generalize to out-of-train data context settings. And of course, since we don't have to worry about the phase issue, we also can in principle synthesize high-quality audio. So realizing this, Blau and Bonada used the vocoder representation of speech to train a generative model for speech synthesis. And Engel, more recently, proposed this differential digital signal processing pipeline, which works on a parametric model controlled by a deterministic autoencoder. So before we discuss more about our model, at the heart will lie the data set, because we are ultimately limited by how good our data set is. So we use the Good Sounds data set, which is an open source data set from the MTG by Romani Picasso. And the data set is basically individual note and scale recordings for 12 instruments. And we work with the violins specifically, and with on the fixed mezzoforte or medium loudness, and with the 4th octave, which represents the standard pitch playing range. And it's played by 4 violins on a single violin, trained on 1,000 flames. So one question you might have is why we choose the violin specifically. So the reason for us to work with the violin is it's very popular in Indian music, especially in South Indian Carnatic music, which is a music form in South India. It's where it is commonly used as an accompaniment to shadow the singer. So for example, when the singer is singing something, the South Indian Carnatic violinist will try to follow the singer's pitch track and other things as well. But yeah, it's a very famously used accompaniment in Carnatic music. And it has a human voice, like very rich timbre, and has the ability to produce a continuous pitch. So to provide some further motivation in how a parametric in the use of a parametric method, we perform a simple generalization experiment to see. So this is a non-parametric reconstruction case. So this is essentially the work by Sarafin, Casey, and Roche. So we use the same network as they did, where we use an autoencoder to model the magnitude spectrum. And what we do is we train it on these 6 nodes, we train it on these 7 nodes from MIDI 60 to 66, and we include and exclude MIDI 63. So what we want to see with this is if that the spectrum is a generic representation which when used, the network can the network generalize to MIDI 63 if it has not been trained on MIDI 63. So so this procedure is repeated frame-wise, and then you invert the obtained spectrogram to obtain the audio. So these are the spectrogram shots. So this is the input MIDI 63 note. And if you train the autoencoder on MIDI 63, it is reconstructed reasonably well. And you can also listen to the audios. So this is the input MIDI 63 note. So this is the reconstruction when you also train the autoencoder with MIDI 63. Is reasonably good, but if you exclude MIDI 63, you can obviously guess from the spectrogram itself that there is a considerable, that's going to sound considerably different than these two, and it indeed does. The timbre is quite different from these two notes, and the reason for that is because the autoencoder essentially is not something that is not a network that can generalize very easily, especially with the spectral representation. So the autoencoder, when trained on MIDI 63, knew what to expect when fed with MIDI 63 frames. But when not trained on MIDI 63, the autoencoder did not know what to expect. So it produced what it felt was the most optimal MIDI 63 spectrogram in terms of the mean squared error, which clearly is not the actual audio because you saw the timbre was destroyed considerably. So a bit more on the parametric model we employ. So ours is we work with the same frame-wise modeling procedure, and we build on top of the harmonic plus residual model by Serra. And currently we neglect the residual. So the harmonic plus, just a quick recap of the HPR model. So the HPR model breaks an audio signal into a sum of sinusoids and a residual signal. So the sum of sinusoids just generally represents the harmonic content of the audio, and the residual represents that portion of the audio which cannot be represented by harmonics. So for example, the noisy portion of the audio. So explicit in our violin case, the noisy portion of the audio is the scratchy sound the bow makes when you slide it against the strings. So this is the harmonic plus residual model where you extract the harmonic, the harmonics and the corresponding magnitudes. Then the next step, we build on top of this harmonic plus residual representation with the true amplitude envelope algorithm. So this algorithm is an estimate for the spectral envelope of the audio, of the harmonic portion of the audio. So the TA algorithm was initially by AMAAI in '79, but the original paper was in Japanese. So Robel and Rodet transliterated the paper from Japanese to English, but yet there was no open Python source, no open source implementation. So we reread the paper and we have made an implementation following the instructions in Robel and Rodet for the algorithm. So what the algorithm essentially does is it gives us an estimate of an envelope which passes through the peaks of the harmonic spectrum. So for those of you who have worked with speech before, this might seem very identical to the source filter model for speech production, and it indeed is. It is indeed a source filter model inspired representation. So the envelope used in the source filter model is actually the Lifted Kepstra. So the problem with using the simple Lifted Kepstra is that it is an envelope that passes through the mean spectra and not through the spectral peaks. But when we want to model the instrument, we are specifically interested in the harmonic values at the peaks. So the TA algorithm works with the same cepstral envelope, but performs what is called iterative cepstral lifting to push the mean envelope to follow the peaks instead of the mean energy. So ultimately, it gives us a smooth function that is parameterized by the cepstral coefficients, and one which we can sample at the harmonic locations to obtain the harmonic amplitudes. So here's an example of the audio represented by this parametric model. So this is an input note. And this is the harmonic version, harmonic parametric representation as described, which is reasonably good, but an important thing to notice is it misses the scratchy sound of the residual because we do not model the residual in this case. So here is an example of the spectral envelope across different pitches. So an immediate thing to observe from this plot is that there is considerable variation as a function of pitch. So again, coming to the source filter model analogy, the source filter model actually assumes some kind of independence between the source and the filter. But here we see that the filter, which is the spectral envelope, actually has some kind of variation across pitch. So we hypothesize that the two reasons for this could be that there is actually the dependence of envelope on the pitch itself. So that attributes to the fact that the source filter model might not actually hold for the violin because the source and the filter are coupled. So for example, when you play the violin, when you play the strings on a violin, it is connected to the violin body. So there is some kind of internal feedback mechanism which could cause the dependence of one on the other. Or the other reason is due to the variations imposed by the estimation of the spectral envelope by the TAE algorithm. So we are currently investigating this in our work now, but at the end of the day, what the TAE estimate of the spectral envelope gives us is a smooth function which is easily parameterized by the cepstral coefficients, and which is one we can use to estimate the harmonic amplitudes. So just a quick recap of the generative models we'll use. So we primarily work with the variational autoencoder. So the variational autoencoder builds on top of an autoencoder, which is a neural network which tries to obtain an optimal lower dimensional representation of the input. And optimality here refers to the fact that the network minimizes the mean squared error between the input and the output. So the variational model simply enforces an additional constraint on this lower dimensional representation, that of being a normal or a smooth distribution. And the conditional variational model enforces a conditional prior by additionally conditioning on an external variable. So the first question I might have is why we use a variational model over an autoencoder. So an autoencoder actually simply just minimizes the mean squared error. So an issue with that is it does not enforce any smoothness in the latent space. So say, for example, we want to generate audio. We would like to do so by sampling points from the latent space, but the autoencoder enforces no constraint of smoothness. So the variational autoencoder, by enforcing a normal distribution on the prior variable, ensures a continuous latent space from which we can sample points and synthesize the corresponding audio. And why additionally use a conditional variational model? So we just saw that the spectral envelope varies as a function of the pitch. So if we can condition the spectral envelope on the pitch, we can rely on the network to capture the dependencies between the timbre and the pitch. And this will allow for more accurate envelope generation and better pitch control. So this is the network we use. So our network is a simple feed-forward, CVA with simple feed-forward neural networks as the encoders and the decoders. And the input to our network is the spectral envelope parameterized by the cepstral coefficients. And the conditional variable is the pitch, because as we saw, the cepstral coefficient, the envelope depends on the pitch. So because the network input is the cepstral coefficients, one thing to note here is that the mean squared error is actually, in some sense, a perceptually relevant distance in terms of the squared error between the input and reconstructed log magnitude spectral envelopes. So this is in comparison to finding the mean squared error between the spectrograms, where trying to minimize the mean squared error between spectrograms need not produce a perceptually optimal audio. So the main hyperparameters we have in our network are, so we use a beta VA, which represents the trade-off between the reconstruction and the prior enforcement. Just a quick reminder of the loss function here. And the second main hyperparameter is the dimensionality of the latent space, which governs the reconstruction ability. So we perform a few simple experiments to do those. So we would like to explore how good or how optimal this parametric representation is. So we perform two kinds of experiments to do this. So one is the reconstruction, where we omit certain pitch instances during the training and see how well our network can model those reconstructed notes, especially the ones from which we skip during training. And the next is generation, to see how well the model synthesizes notes, because ultimately we are interested in using this network as a synthesizer. So for reconstruction, we have two training contexts. So the first is similar to the previous experiment we had performed by training the network on these 7 notes and skipping the MIDI 63 note. So here is an example of the audio produced. So the experiment is exactly the same as before for the non-parametric case, except this time we work with our parametric representation. So for the same input MIDI 63 note, this is the network's reconstruction, which is reasonably, it's actually not bad because the network has no information of MIDI 63. It only works with the neighboring notes, and it tries to estimate what is the most optimal parametric representation instead of the spectra. And just a quick reminder for how the spectral reconstruction sounded when you skipped MIDI 63. And then the next is a bit more extreme. We only train our network on the octave endpoint. So we only train it on MIDI 60 and 71. And we reconstruct all of the intermediate notes from MIDI 60 to 71. So this plot here shows us the mean squared error for this network trained only on the octave endpoints. And an immediately interesting thing you can see is when you condition on the pitch, the mean squared error is consistently lower than for a network where you do not condition on the pitch. So this kind of enforces our belief that the conditioning captures the pitch dependence of the spectral envelope more accurately. So the other advantage of pitch conditioning that we mentioned was that of continuous pitch control. So where does such a context come? So consider a training scenario like this. So this is a network which has been trained on these blue notes. So these are actually the Carnatic notes. So they are not the same as the MIDI notes, but for the sake of demonstration for this experiment, you can assume that these are the MIDI notes. So now we have a network which has only been trained on these MIDI notes. Now, what if we had to synthesize a varying pitch contour like this? So for those of you who are not familiar with Carnatic music, unlike Western music, does not rely on a fixed pitch grid. It has a variable pitch grid, and it also relies on a lot of ornamentations and variability in the pitch contour. So this is a standard Carnatic gamaka, it's called in Carnatic notation. So there is considerable variation in the pitch. So if you look at these green highlighted zones, the network has been trained on those. So you would expect the network to reconstruct that. But how about this continuous pitch sweep here? The network has not been trained on any of these intermediate pitch zones. So if we were to train if we were to use a spectral representation of audio, and by spectral I mean the magnitude spectrogram, and try to do something like this, we saw that the spectral representation does not generalize. So it will fail to model this kind of varying pitch contours. But with our parametric representation, we can only train the network on these fixed notes and in principle generate the entire continuum of pitch in between them. So for an input pitch contour like this, this is our network's reconstruction of the same. So an important thing again to remember here is our network has only been trained on these discrete pitches. It has not seen these intermediate values. So what we hope for is that the conditioning allows the network to generate what it feels is the most optimal parametric representation for the intermediate pitches. And from that parametric representation, we can in turn reconstruct the audio. So the experiments we discussed were the reconstruction ones, but ultimately we do want to synthesize audio as well for use as a generative synthesizer. So because we're using a variational model, the generation portion is quite simple. We just have to sample points from our latent space and pass the pitch as a conditional variable to the decoder. And that gives us a sequence of these spectral envelopes. So to generate an audio, we have to sample multiple such points from the latent space. So how do we do that? One immediate thing we could do is keep the same point and keep the latent space point fixed and sample the same envelope across. But that would sound extremely synthetic because of the lack of variation in the spectral envelope and in the pitch contour itself. So what Blau and Bonada suggest is perform a small controlled random walk in the latent space. So that would introduce some minimal variations in the spectral envelope and hope to introduce these variations in the audio itself for additional naturalness. So this is an example of a network generated note. It's not good. It does not sound like an acoustic violin. And what we feel the reason for that is ultimately the only difference between generation and reconstruction lies in the fact of how we sample the points from the latent space. So for the reconstruction experiment, we have the input sequence of frames, which we project into the latent space. And that sequence, the ordering of the points in the latent space is controlled by the frame sequence of our input audio. So when we follow the same order in the latent space, we can reconstruct the audio reasonably well, as you heard from the previous reconstructions. But however, this trajectory, what we feel, is not something that can be approximated by a simple random walk. It's much more complicated than a random walk. So random walk is still not enough to introduce that amount of variability in the generated audio. So for a bit more like natural sounding violin, we also decided to introduce a bit of vibrato into the tone to see if that would make the tone sound a bit more natural. So it's better than the fixed note, but it still doesn't sound like an acoustic violin. It sounds like one of those synthesizer, one of the violin renderings on a synthesizer you play. So at least summarizing our work, we explored autoencoder frameworks in generative models for audio synthesis, specifically for instrumental tones. And we feel that a parametric representation decouples the timbre and the pitch, and we can rely on the conditional network to model the interdependencies. Pitch conditioning specifically allows the network to obtain the optimal spectral envelope for that pitch, and also allows us to vary the pitch contour continuously, which is a characteristic thing in Indian classical music. But a few drawbacks of our model are we have not modeled the residual so far. So the residual is something that contributes to the perceptuality of the generated note. So that is something we are working on currently. We have also not taken into account dynamics. So the dataset we use has a fixed set of loudness values. However, the timbre might also depend on the loudness simultaneously along with the pitch. And as we mentioned in the start, we don't since we use the same frame-wise modeling based method, we don't take into account the temporal evolution. We only model the sustained portion. So these are the drawbacks of our model. So just a concluding thought. So this was our first step towards building a system that can synthesize these melodic elements from Carnatic music. So given the pitch contour as an input, we would like to synthesize expressive Carnatic music. So here's an example of a Carnatic piece. Which is clearly very challenging to synthesize. So to the best of our knowledge, we have not come across people coupling the use of a parametric model with the neural synthesis framework, especially the one we propose, that is the use of a source filter inspired model. And all of our code and audio examples in this presentation are openly available in our GitHub repository. So thank you for your time. I'll be happy to answer any questions you'll have. here are the references in use, and here are the descriptions of the audio examples played. So yeah, thank you.
Thanks so much, Krishna. Very interesting presentation. I think there's been a few questions in the chat. Maybe you could have a look.
Yep, I'll have a look at them.
Wait from June, I think.
So the first question is the Dataset slide models mentions that the model is trained on 21 millisecond segments, and how did you render the full note samples? So correct, the dataset is indeed trained only on these 21 millisecond frames. But what we do is we feed in the input frames from the audio in the same order, and we reconstruct the frames from the input audio, and then we invert the reconstructed either the spectrogram or a parametric representation to obtain the audio from that. So does that answer your question for the first one? Okay, there's another question also. So please correct me if wrong. The parametric model you implemented does not model the dependency between the pitch and the spectral envelope, and you resort to the CVAE hoping that it can capture the dependency. Correct. So the source filter, our parametric model is indeed a source filter model inspired representation. So in speech, you implicitly assume the independence of the source and filter, and that is a good enough assumption for at least a few small frequency shifts. So, but in our case, it is not actually independent of each other. So we hope for the network to model the interdependencies between both. If so, because the derivation of timbre represented as the Kapstein coefficients is still not dependent on the pitch, the dependency is not explicitly modeled. So also this also is a good point. So we are still experimenting on what we feel is the reason for this dependence. So as it mentioned in the slides, this dependence could arise, one, because of what we feel of the non-independence of the source and filter for the violin audio. But we have come across some literature stating that the source filter model actually might indeed hold for the violin audio. But what happens is that the violin body resonances are extremely narrow. So when we are estimating the true amplitude envelope algorithm, one of the steps in the algorithm is actually to subsample the harmonic spectra at the fundamental frequency. So if you have a harmonic spectra whose fundamental frequency is small, you subsample it, you have more points to sample the envelope from. But if you have a harmonic envelope whose frequency is large, then you only have a few points to estimate the envelope from. So what we are experimenting now in is whether this estimation procedure is what is causing this perceived dependence of the spectral envelope on the pitch. So on evaluation using MSE, how to verify if MSE between the Kapstein coefficients correlates well with the perceptual distance without a subjective listening test. On page 20, demonstrating audio generation. Oh, okay, first question then. So you can't. So you have to perform extensive tests to say that to comment whether the Kapstein coefficient correlates well with the perceptual distance. However, what we can comment on is that the minimizing the MSE between the Kapstein coefficients is indeed more optimal than minimizing the MSE between the spectral representation. So that is what we can say for sure. So, and this is research even in speech. So even in the source filter model, the estimator tries to find out an envelope that tries to find out a spectral envelope that minimizes the mean squared error between the estimated spectral envelope and something which can approximate the speech spectrum. So using the CCs is obviously better. Minimizing is better than minimizing the MSE for the spectra. But to say whether it correlates with perceptual distance, you have to perform some subjective listening tests. So on page 20, okay. Demonstrating audio generation. Is the pitch condition changing over time to create effect of vibrato, or you only change Z over time? Yep, good question again. So here, so we can vary the pitch contour continuously. So we change the pitch contour to that of a vibrato contour to synthesize the vibrato note. So yes. So yeah, I think that has answered all the questions. If I fail to answer any of them, could you please let me know which ones I fail to answer, so I'll try to attempt them again. Otherwise, any other questions, I'll be happy to answer.
Thanks, Krishna. I was also wondering, if you're testing your generation, basically you're doing just subjective listening, right? Would there be a way to formalize this a bit? Let's say through classifier. I think June has done something similar.
Oh, so let me just if I'm understanding what you're saying correctly, what you're saying is if you can quantify the subjectiveness of the generated audio through some external means. Is that what you're trying to ask?
Yes, indeed. Yeah. Yeah, if you're trying to, maybe you could train a classifier between violin sounds and another instrument and see if it would pick it up or not.
Okay, so that's a good idea, but why I feel that might not work optimally is because, so like considering the example you said, you want to train a classifier which wants to, okay, so say suppose the generated note is violin or not, but saying what constitutes a violin is a very large space. So for example, we performed very simple listening tests with trained Carnatic violinists for our task, and they gave us some very interesting feedback that your audio sounds like does not sound like an acoustic violin. It sounds like a very monotonically, or as if a robot was playing an electronic violin. So it sounds very similar to that timbre. So if you want to quantify the generation for one class of instruments, it might be very tough. But if you were to maybe split it to a much more detailed categorization, then maybe that could work. Like classes, yeah, just quickly, what I mean to say is, if you're saying it's a violin or not violin is too gross of a generalization, yes, is what I feel.
Yeah, I understand. The violin is a very tough sound to generate. I feel like even the big, like Logic Pro has some violin sounds, and even then, if they're sampled sounds, still they don't sound super realistic. So it's it's a tough problem that you're trying to tackle.
Yeah, violin is it has a very rich timbre. So yeah, so that's so the reason for one of the motivations for our work, which we pointed in the last was, we wanted to see if we could build a system that could shadow a singer as an accompaniment system. So if you could just say the singer singing and you extract the pitch contour, then you can feed that pitch contour to hypothetically our model, and our model can generate a violin accompaniment with a continuously varying pitch contour. That was like a very simple. So the reason for doing this is we wanted to see if we could generate accompaniments, but we realized that the generation is not as simple as we thought it would be. Like just a simple approximation does not generate really good. Actually, doesn't sound good violin at all. It sounds like something very synthetic.
Interesting. So what are your next steps in this?
So what we are currently working on now is the most immediate part was to incorporate the residual, which we felt was a very important thing. So for example, in a violin sound, all of our sounds lack the residual modeling. So you will not hear the scratchy sound of the bow when the notes are being reconstructed. So that we feel is an important attribute, important characteristic of the naturalness of the naturalness of the violin sound. So we are trying to use a similar source filter representation for the residual as well, and seeing if we can model the residual and model the harmonic and residual together. So that those are some of the problems we are exploring currently also.
Very cool, very cool. Well, thank you so much for talking. I don't know. Oh, I think maybe Jim has another message.
Yeah, I'll just see the question. Thank you for clarifying. Right, thank you. And have you tried to train the model on a data set with richer variation? Example, different loudness levels. This is a very, very, very good question. Have you tried to train the model on a data set with richer variation? So sadly, there does not exist a model with richer variation than these two. So we are interested in the generation of instrumental tones, right? So the two largest data sets in existence, the largest data set is NSynth, but the problem with NSynth is NSynth lacks expressivity. And also, so they mentioned that the NSynth is characterized by the MIDI pitch, by the MIDI velocity, but the MIDI velocity is not a very good indicator of the loudness of the generated note. And especially for the, so NSynth has three classes of instruments if you have used it. So it has acoustic, acoustic instruments, electronic instruments, and electronically synthesized instruments. So especially for the acoustic ones, and since we're working with the violin, which we would want to model acoustically, the loudness the MIDI pitch is not very well described in NSynth. So there is, and for the good sounds dataset which you use, it's on a fixed, like the medium mezzoforte loudness. So this is a very good question. And for this, we are currently trying to see if we can record our own data set of violin notes, which are characterized by different playing styles, different loudness, and then within a controlled setting, see what exactly you suggested. Like, how does it perform when you try to train it with more degrees of freedom? So, does that answer your question? Sure. Once our work is done, we plan to make our data set open source for everyone to use in the AMAAI community. So sure.
Great. Thanks again, Krishna. Next week, there won't be a webinar because I have a guest speaker in my AI class at this time slot who is actually talking about NLP solutions. So it's a company in Singapore/Belgium who have developed a chatbot and do all sorts of AI services here. So if you would want to follow in, then just send me an email and send you the Zoom link. And also, if you want to present your research in this webinar, let me know and I'll schedule you in. Okay, that's all for me. Thank you again, Krishna, and I hope to see everyone again in a future seminar.
Thank you, everyone. Stay safe.